some pendulums are not simple. Okay, remember, simple pendulum is a point mass on a string. Okay, so we're going to see a meter stick, okay, pivot about one end. Okay, this would be a ring or a hoop, right? You could take like an empty roll of tape, okay, put your finger there and just kind of oscillate it back and forth. Okay, so a hoop or a thin ring. Okay, and you can take a shoelace and your shoe and oscillate that back and forth. All right, so these are called compound pendulums. Okay, some books call them compound, some books call them physical pendulums. We'll stick with the word physical pendulum. Okay, so we want to see whether or not a physical pendulum is a simple harmonic oscillator. All right, so imagine I have this shape. So this is like a big chunk of plywood. Okay, for now, just think of this as two-dimensional. Okay, so a big chunk of plywood, and I have a nail through it, and it's frictionless. Okay, but it can rotate about that axis on a nail. All right, and I want to find the period of oscillation. Okay, so in the video we just saw, okay, this thing is definitely periodic motion. Okay, as long as there's no friction or there's not much friction on the pivot point, okay, it's periodic motion. Okay, it repeats itself in regular time intervals. Okay, but is it simple harmonic? Meaning, are the solutions for when I pull it back to some angle theta? Okay, does it go as theta max cosine or sine of omega t? Okay, so let's find the period and see what parameters it depends on. Okay, so when we did the simple pendulum, we used Newton's second law. So I'm going to use Newton's second law as well, but I'm going to use it in rotational form. So we're going to calculate net torque equals I alpha about the axis of rotation. Okay, so I have to draw the forces that act on this physical pendulum. So M, okay, M is the mass of the chunk of plywood. Okay, all right, and then here's the center of mass. That point right there, okay, that's the center of mass. All right, and so the weight, okay, mg, acts at the center of mass. Right. The other force that acts on the chunk of plywood is the support force. So the nail, okay, is pushing upward to prevent the plywood from falling to the ground. Okay, so those are the only two forces that act on the mass. All right. Now, which of those forces exert a torque? Well, the normal force doesn't exert a torque because it passes through the axis of rotation. Okay, so the only thing that causes a torque is mg. All right, so in this picture, okay, it would be a counterclockwise torque, right? Because the torque due to mg would tend to rotate the system counterclockwise. Okay, so remember, if you just take this piece of plywood and just let it rest, okay, this center of mass is just going to lay below the support point. Okay, that's where it would rest all day. All right, so you have to lift it up. Okay, you lift this thing up from here. Okay, and then you're going to let it go. All right. Okay, so the only force that causes the torque is mg. So let's calculate the torque. So here is, right, that's my line of action, and then I have to draw a perpendicular line from the axis of rotation to the line of action. Okay, that's that line. That's my moment arm. All right. Now, another distance I put in here is I'm using the distance d. That distance d. So that distance d is the distance from the pivot point to the center of mass. That's my distance d. Okay, from the pivot point to the center of mass. Okay, theta is the angle from the vertical, so that's theta. Okay, that one's theta. Okay, my moment arm right there, that's opposite the right angle. That's opposite theta. So the moment arm, our perpendicular, is d sine. Okay, so that side right there is d sine. Okay, so the torque about axis A is force, mg, times the moment arm, d sine. Okay, but I have to include that minus sign. Okay, why do I include the minus sign? Well, if we ignored the minus sign, if that minus sign wasn't there, okay, that would say that the torque due to mg would keep this thing rotating counterclockwise. Okay, and that makes no sense. Okay, we know that that doesn't happen. All right. Okay, now the other reason the minus sign is there is if I drew this whole picture like this, if I drew it on the right side, okay, now the torque due to mg would be a clockwise torque. Okay, so the torque due to mg changes direction whenever the center of mass passes over the equilibrium, or the equilibrium point for the center of mass. Okay, so an mg is on the left side. Okay, it's a counterclockwise torque. When that center of mass passes over to the right side, the torque due to mg is now clockwise. So the minus sign indicates that mg d sine theta is a restoring torque. Okay, it's always in a direction to restore, okay, the center of mass back to its equilibrium position. All right, so you can also think about it as if I just had this thing resting, there's the center of mass. If I move it off to the right, mg, the torque due to mg wants to bring it back. If I displace it to the left, torque due to mg wants to bring it back. Okay, so it's the exact same treatment. Okay, this whole business still reminds you of the mass in a spring. Okay, and there's your restoring force. Okay, remember your Hooke's law, restoring force, same idea. Okay, so here is Newton's second law, net torque equals I alpha. Okay, so my net torque is minus force times moment arm, so minus mgd sine theta. Okay, and that's equal to I alpha, so I'm going to solve this for alpha. Okay, so divide both sides by I. All right, and then alpha is a second derivative with respect to theta, so right there I put in alpha. Okay, and you're going to see the pattern, a pattern. It's the same steps we did, okay, for the mass and spring and for the simple pendulum. Is we had the second derivative over here. Okay, so you have a function. Okay, you have a function. You take two derivatives. Okay, take two derivatives, and then you get minus some constant, all right, times something back. Okay, now let's make sure what I have here is a constant. Okay, so mass is a constant, g is a constant, d is that distance, okay, it's a constant, and I is just the moment inertia of that piece of plywood. Okay, now let's look at the units of mgd over I. Okay, so m is mass, g is gravity, d is a distance. Okay, and remember what I is. Okay, remember you can say what I is in this course. Okay, so remember I for point mass is sum of mr squared. So the units of I is mass times distance squared, kilogram meter squared. Okay, so the kilograms cancel. Okay, the m's cancel. Okay, and all you're left is you're left with that 1 over s squared. Okay, left with that 1 over s squared, and then I wrote in the word radian right in the parenthesis for free because it's a dimensionless quantity. And then I look at that and I say, oh, well, that's the units of omega. Okay, so this whole thing, okay, has units of omega squared. Okay, so I'm going to call mgd over I omega squared. Okay, that has units of angular frequency squared. Okay, so then I rewrote this. Okay, now when I write this, okay, I got an omega sitting here. It's like, what's the omega? Well, remember, that's the omega, right? You take the square root, okay, take square root of both sides. There's your omega. Okay, so is this the form for superharmonic motion? Okay, no, because you have a function, take two derivatives, you get minus a constant, which is good, but you don't get the same function back. You get the sine of the function, okay? So that's the exact same thing we had with the simple pendulum. So this thing is not a simple harmonic oscillator. Okay, if I pull it back at 20 degrees, it's going to have a certain period. Okay, if I pull it back at 30 degrees, period is going to depend on the amplitude. Okay, so we don't want that. So what we do is we force it to be a simple harmonic oscillator, and we use the small angle approximation. Okay, so for small angles, sine theta is approximately equal to theta. So where I have sine theta, I put in theta. Okay, so now it is a simple harmonic oscillator, and we know that this has the form, or this has a solution of theta max cosine or sine of omega t plus phi, where we have to put the where part, right, where omega was that mess. Okay, mass of the object. Okay, got to be careful. That d, okay, d stands for do not be confused. Okay, that d is a specific distance. Okay, so it's just from the pivot point to center of mass. Okay, that's no big deal. Okay, so we get omega, and then we know the period is always 2 pi over omega. So the period is 2 pi divided by that whole square root thing. Okay, so flip the square root, and that gives me the period for the physical pendulum. Okay. All right, so I think I have these on the equation sheet. I say that they're good to know. Okay, sometimes they'll pop up out of nowhere from in like the 196 class. Okay, they're kind of good to know, but that's okay. Okay, so some of the parameters it depends on. It depends on the shape. Okay, whether you're oscillating a meter stick or a ring. Depends on the mass. Depends on what planet you're on. Okay, and depends on that distance from the pivot point to the center of mass. Okay, now we said several times throughout the semester that it's good to check your answer. Okay, well, how do you check your answer? Well, one way is to check the dimensions. Okay, so you check all the units and you would find that indeed you get dimensions of seconds. Okay, another thing you can check is you want to see if this reduces to the simplest case in the limit where something gets small or big or goes to 0 or infinity. Okay, so let's check to see if that expression works for a simple pendulum. Okay, because this should give us the period of a simple pendulum in the limit where that big chunk of plywood now looks like a point mass far away from the axis of rotation. So here's our simple pendulum, and I'm going to use this expression here to calculate the period. Okay, so here's my I. Okay, there's my axis A. So I have to calculate the moment inertia about axis A, okay, for the simple pendulum. Well, simple pendulum is a point mass. So a sum of mr squared. So m is the mass of the point mass, and the distance from the pivot point to the center of mass, right? So, okay, or I should say, the distance from the pivot point to where that mass is L, and squared. So that's my I, moment inertia about axis A. This m, that m is the mass of the point mass. Got that? There's the G. Got that? And D. Okay, remember D above was the distance from the pivot point to the center of mass. Okay, that was my distance D. Pivot point to the center of mass. Here's my pivot point. There's the center of mass of my point particle, and that distance is L. Okay, so the mass drops out, one of the L's drop out, okay, and it reduces to a simple pendulum. Okay, so let's say if you forgot that expression, okay, but you knew that one, you could always use the physical pendulum expression to give you the period of a simple pendulum. So we just found the expression for a physical pendulum. Okay, now we're going to pivot a thin hoop, okay, about a nail, and we want to find the period of oscillation for the thin hoop, or call it a ring. Okay, so that's our starting point. We have to remember what each quantity represents. Okay, so I is the moment inertia about axis A. Okay, m is the mass of the ring, and D is the distance from the pivot point to the center of mass. Okay, so there's the center of mass. Okay, we don't need to draw the forces. Okay, but the old picture we had. Okay, right, there's the center of mass. There's mg. Here's the center of mass. There's mg. Okay, so that's the distance D. So the distance D is just the radius. Okay, so that distance D is the radius. Okay, so I'm going to calculate the numerator. Okay, so remember, it's the moment inertia about the pivot point. Okay, well, the moment inertia about the pivot point for a ring, okay, we'll use the parallel axis theorem. So the parallel axis theorem says moment inertia about axis A is I center of mass plus mh squared. So moment inertia about center of mass is mr squared plus mh squared, and h is the distance between the center of mass axis, whose moment inertia we know, and our new axis. Okay, so the perpendicular distance between those two axes. So you have a line coming out of the screen. You have this line here coming out of the screen. Okay, the distance between those 2 points. Okay, distance between those two axes, h, is just the radius. Okay, so there's our moment inertia for the hoop. We had done that previously in the notes. Okay, so I'm going to put that in for my numerator. Okay, I have my denominator, okay, mgr, right, mgd, where d is r. Masses drop out, one of the r's go away. Okay, now 2 times the radius is the diameter. Okay, so I already have too many d's floating around, so I'm going to use a little d for the diameter. And then what I did here is I just factored out everything that was a constant. Okay, so the 2 pi is constant. Okay, the g is constant. I brought that outside. So the only variable or parameter is, or I should say, the only variable is the diameter of the hoop. Okay, so this says that the period, okay, goes as the square root of the diameter, right? So we'll see, hopefully in the lab, that if we have a ring, okay, has a certain diameter, right, it'll have a certain period. We'll call that T initial, okay? Then what we'll do is you'll take a huge ring, okay, and you're going to increase the diameter by a factor of 9. So instead of a diameter of D, now you have a diameter of 9 times that, okay? And if you look at how does the diameter affect the period, okay? The period goes as the square root of the diameter. So the diameter increases by a factor of 9, okay? When I stick the 9 in there, the period goes up by a factor of, period goes up by a factor of 3. Okay? So diameter goes up by 9, period goes up by the square root of 9, which is 3. Okay, so the period triples. All right. So what you'll actually do in lab is you'll have a ring pendulum, okay? You'll pivot it around a point, right? You can measure the period, okay? You know the distance d, and you can actually use that to find little g. Okay, so it's another way of measuring little g, okay? Obviously, the easiest way was just with a simple pendulum, but you can also do it with a ring pendulum. Not to make it confusing, but in the lab, when we write this in the lab, okay, I think I use capital D, okay, for diameter. Okay, this is going to be in our lab. Okay, so capital D, all right? And you're going to verify that this has the form, okay, some constant times D to the n, right? Well, what is that constant? Well, that constant is 2 pi over square root of g. Well, if you square both sides, you get 4 pi squared over g. Solve that for g. Okay. In C, in lab, you'll get an experimental value for C, and then you can calculate little g and compare it to our 9.8.